Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the look ahead carry adder. Now in the previous video, we learned about the ripple carry adder and we have seen that in this adder, to get the stable output, we have to wait until the carry propagates through each stage. Let's say for each full adder, if Ts is the propagation delay for getting the sum output and Tc is the propagation delay for generating the carry output, then for the n bit adder, the final sum output will be available at n minus 1 times Tc plus Ts time. While if we see the carry output, then it will be available at n times Tc time. So as you can see from these expressions, as the number of bits n increases, then the overall propagation delay of the adder will also increase. So that is the limitation of this ripple carry adder. Now in this adder, all the input bits or these A's and B's are applied simultaneously to all adders. But here, each adder has to wait for the valid carry from the previous stage, and that limits the speed of the addition. So let us see how to overcome this problem. So let's say we have the combinational circuit which can generate the carry bit for each adder from the input bits. And these carry bits, that is C1, C2, C3 and C4, are generated at the same time. So if we can design such combinational circuit, then each full adder does not need to wait for the carry bit from the previous stage. So the similar sort of concept is also used in this look ahead carry adder. So of course, the exact circuit of the adder is bit different, but the design philosophy is very similar. So to understand this carry look ahead adder, first let us understand when the particular full adder block generates the carry bit. So in this full adder block, there are only two ways this carry gets generated. One is the block itself generates the carry based on the input combinations, and second is it propagates the incoming carry to the next stage. So let us understand these two terms, that is carry generation and the carry propagation, because these two terms will help us in designing the combination logic of the adder. And for that, let us consider this circuit of the full adder. So in this circuit, the carry output of this OR gate will be high when any of the AND gate output is high. So first, let us consider this lower AND gate. So this lower AND gate represents the carry generation. So now if you see the inputs of this AND gate, then they are A and B. So the output of this AND gate will be high when both the inputs A and B are high. That means whenever both the inputs of the adder are high, then irrespective of the carry input from the previous stage, the carry will be generated for the next stage. That means if this AND gate is high, then the irrespective of the output of this upper AND gate, the output of the OR gate will remain high. So that is the carry generation. And let us denote it as a G. So this G will be equal to 1 when both inputs A and B are high. That means this G is equal to A dot B. So that is the carry generation. Similarly, now let us see the next AND gate. So the input to this AND gate are A XOR B and Cin, where the Cin is the input carry from the previous stage. So the output of this AND gate will be 1 when both inputs Cin and A XOR B is 1. Or in other words, when we have a carry from the previous stage, then it will propagate to the next stage only when this A XOR B is equal to 1. So if this A XOR B is equal to 0, then this input carry won't propagate to the next stage. That means the carry from the previous stage will propagate to the next stage whenever this A is equal to 1 and B is equal to 0. Or the second case is when this A is equal to 0 and B is equal to 1. Or in other words, we can say that this carry will propagate to the next stage when this A XOR B is equal to 1. So this function A XOR B defines the carry propagation, and let us denote it as the P. So this P is equal to A XOR B. So that is the carry generation and the carry propagation functions for the full adder. So now let us consider this 4-bit ripple carry adder once again. So in this 4-bit adder, if we just consider the first adder, then the inputs are A0 and B0, while the input carry is equal to C0. So here, the output of this lower AND gate is equal to G0, while the output of this XOR gate is equal to P0. And if we see the output of this upper AND gate, then it is equal to P0 dot C0. So for the first full adder, this carry output C1 will be high whenever this G0 is high or this P0 dot C0 is high. That means this C1 is equal to G0 plus P0 dot C0, and the sum output S0 is equal to P0 XOR C0. So this carry C1 will be given to the next stage. So in the next stage, the inputs are A1 and B1, while the input carry from the previous stage is equal to C1. So here, the output of the XOR and the AND gate are P1 and G1, while the output of this upper AND gate is equal to P1 dot C1. So for the second stage, this carry output is equal to 1 when either G1 is high or this P1 dot C1 is high. That means the C2 is equal to G1 plus P1 dot C1. Now we have just seen that this C1 is equal to G0 plus P0 dot C0. So after the further simplification, we can write this C2 by this expression. So this expression shows when the carry output C2 will get generated. Similarly, here this S1 will be equal to this P1 XOR C1. So here this carry output C2 will be given as an input to the next stage. So for the next stage, the inputs are A2 and B2, while the carry from the previous stage is equal to C2. So in this third stage, this carry output C3 is high when either G2 is high or this P2 dot C2 is high. That means C3 is equal to G2 plus P2 dot C2. Now earlier, we have seen that this C2 can be given by this expression, right? So if we further simplify it, then we will get the expression of the C3. So now this carry output C3 is given as an input to the final stage. So for the fourth stage, this carry output C4 is high when either G3 is high or this P3 dot C3 is high. Or we can say that this C4 is equal to G3 plus P3 dot C3. Now we have just seen that this C3 can be given by this expression. So if we further simplify it, then we will get the expression of the C4. And of course, this S3 is equal to this P3 XOR C3. So in this way, we got the four expressions of this C1, C2, C3 and C4. And it defines when these carries are generated. So if you see all these expressions, then they are in terms of this Pn, Gn and C0. So in short, all these expressions do not depend on the carry from the previous stage. So in all these expressions, Gn corresponds to An dot Bn of the nth stage, while the Pn corresponds to An XOR Bn. And for the each stage, these G and P can be implemented using one AND gate and one XOR gate. So overall, if we can implement these four expressions using the combinational circuit, then we can easily generate the carries for each adder. So if you see all these expressions, then they are in the sum of product form. So in each expression, the product terms can be implemented using the AND gates, and their summation can be carried out using the OR gate. So if you see the logic circuit of this 4-bit look ahead carry adder, then it will look like this. So as we have seen, this is the expression of the C1, and as you can see, it can be implemented using 2-input AND gate and the 2-input OR gate. Similarly, this is the expression of the C2. So to implement this function, we require 2 AND gates and 1 OR gate. So here, one AND gate is a 2-input AND gate, while the other one is the 3-input AND gate. And as you can see, here we require the 3-input OR gate. Likewise, this is the expression of the C3. So it can be implemented using 3 AND gates and 1 OR gate. And lastly, this is the expression of the C4. So as you can see, to implement it, we require 4 AND gates and 1 OR gate. And in this case, we require the 5-input OR gate. So as you can see, if all the carry generate and the carry propagate terms are readily available, or in other words, if all the Gn and Pns are readily available, then we can implement this circuit in just 2 gate levels. So this is the combinational circuit of the carry look ahead adder. So let us represent it with the single block. So as I said, all the GNs and PNs can be generated using one AND gate and one XOR gate. Now we have also seen that for the each stage, the sum output Sn can be given as Pn XOR Cn. So using one XOR gate for each stage, we can also generate the sum output. So this is the overall logic circuit of the 4-bit look-ahead carry adder. And now let us see in this adder after what time we will get the stable output. And let us also compare its overall propagation delay with the ripple carry adder. So here the output of this carry look-ahead logic will be available after 2 gate delays. So this is the 1 gate delay and this is the second gate delay. That means as soon as we apply these PNs and GNs, then the output of this carry look-ahead logic will be available after 2 gate delays. And for the generation of these GNs and PNs, we require 1 gate delay. That means as soon as we apply all the inputs A and B, then the GNs and PNs will be available after 1 gate delay. So we can say that the carry output of all the adders will be available after 3 gate delays. That means these C1, C2, C3 and C4 will be available after 3 gate delays. And to generate the sum output, we require one more XOR gate. So the sum output of all the bits will be available after one more gate delay. That means overall, the valid stable output of this look-ahead carry adder will be available after 4 gate delays. So for a time being, let's assume that all the logic gates in this adder has the same propagation delay. So with that assumption, the output of this look-ahead carry adder will be available after 4 gate delays. And now, let us compare it with the 4-bit ripple carry adder. And here, we are assuming that this is the circuit of the each full adder. So in the previous video of the ripple carry adder, we have seen that for the AND bit ripple carry adder, the final carry output is available after T XOR plus 2n times TP time, while the final sum output is available after this time, where this T XOR is the propagation delay of the XOR gate, while the TP is the propagation delay of the AND gate and the OR gate. Now let's assume that this T XOR is equal to TP, or in other words, when the propagation delay of each logic gate is same, then final carry output is available after 2n plus 1 gate delays, while the final sum output is available after 2n gate delays. So if we consider the case of the 4-bit adder, then the final output will be available after 9 gate delays. On the other hand, for the look-ahead carry adder, the overall propagation delay was 4 gate delays. That means this 4-bit CLA is 2 times faster than this ripple carry adder. And as we increase the number of bits, then the improvement in the speed is more profound in case of the look-ahead carry adder. For example, if we design the 16-bit ripple carry adder, then the final stable output of this 16-bit adder will be available after 33 gate delays. On the other hand, the output of this 16-bit carried look-ahead adder will be available only after 4 gate delays. That means this 16-bit CLA is 8 times faster than this ripple carry adder. But in this carried look-ahead adder, as we increase the number of bits or the value of n, then the complexity of this logic circuit will also increase. Moreover, we also require the logic gates with the large number of inputs. For example, in this 4-bit CLA, if you see this logic portion of the C4, then it requires the AND gate and the OR gate with the 5 inputs. So in general, if we design the AND bit CLA, then we require the logic gates with n plus 1 inputs. That means as the number of bits increases, then the fan-in of the logic gate will also increase. And as the number of inputs of the logic gate increases, then the cost and the complexity of the logic gate design will also increase. Moreover, as the number of inputs of the logic gate increases, then the speed of the logic gate will also reduce. But of course, here for the simplicity we are assuming that irrespective of the number of inputs of the logic gate, the propagation delay of all logic gates are same. But actually, as the number of input increases, then it also affects the propagation delay. So in short, in this carried look-ahead adder, as the number of bits increases, then the complexity and the cost of design will also increase. So the question is, how to scale up this look-ahead carry adder logic when the n is greater than 4. So there are a couple of ways by which we can achieve that. So for example, if you want to build the 16-bit adder, then instead of using the 16-bit CLA directly, what we can do we can use the block of 4-bit CLA and we can cascade such blocks to build the 16-bit adder. So this cascading is similar to the ripple carry adder, where the output carry from the one stage is given as the input to the next stage. And this design has the best of both worlds. So it is less complex than the 16-bit CLA itself, and its propagation delay is also lesser than the ripple carry adder. So for the usual 16-bit ripple carry adder, the stable output is available only after 33 gate delays, right? On the other hand, in this design, the output will be available after 12 to 13 gate delays. So as we have seen, for the 4-bit CLA, the carry output is available after 3 gate delays, while the sum output will be available after 4 gate delays. That means the carry output of this first stage will be available after 3 gate delays. So as soon as the next stage receives this incoming carry, then it will generate the output carry after 3 more gate delays. That means this C8 will be available at 6 gate delays. Likewise, for this third stage, these C12 will be available at the 9 gate delays. And once this C12 is available, then this fourth stage will generate the carry at the 12th gate delay. So as I said, the sum output of the CLA is available after 4 gate delays. So once the final stage receives this incoming carry after these 9 gate delays, then it will generate the sum output after 4 more gate delays. That means this final sum output will be available only after 13 gate delays. So as you can see in this design, the final stable output will be available after 13 gate delays. So if you compare it with the conventional 16-bit ripple carry adder, then this design is 2.5 times faster than the ripple carry adder. But in this design, each block has to wait for the incoming carry from the previous stage. So if you further want to increase the speed of the addition, and if we can afford little more complexity and the cost of the design, then this is the another design. So here once again, the 4-bit CLA blocks are used. But here, the carry for each block is generated using this carry look ahead logic. So basically, here the carry look ahead logic is implemented in 2 stages. So here, each 4-bit CLA has its own carry look ahead logic, and on top of it, there is a one more carry look ahead logic block which generates the carry for each block. So if we compare this design with the 16-bit ripple carry adder, then it is 4 times faster. So this is more standard approach for designing the 16 or 32-bit adder using this 4-bit CLA blocks. So in this way, by using the hierarchical approach, we can build even 16 or 32-bit adders. So that's it for this video, and I hope in this video you learned about this look ahead carry adder. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.